Greetings, please watching this video or join the lectures. Anyway, welcome. This picture, my name is User. Maybe if you just looked from a video previously, then maybe you will know what I'm talking about. And what topics for I keeping the recording of the videos. So anyway, today's video topic will be just the summarizations of the previously we learned before we start new lectures. So the semi-condutors. Of course, we know what, maybe I hope you or you guys know what is the semi-condutors. The semiconductor may be somewhat the medium part of between the insulators and conductor like metal. So between of these two parts there is semiconductors. By how we compose the components of the semiconductors, we can look at P-type silicons or semiconductors and N-type semiconductors. So by these two types, we can make the first P-N junctions, in short, diode. And secondary, one more thing of the P-N junction, and using the method of how the P-N works, it will become the BJT, bipolar junctions transistor. And for the last, third, PET, field effect transistors. So for the last class and previous videos, we learned, we just focused on the PN junction, insured diode, and the PET, FET, MOSFET. So there are many kinds of MOSFET. So actually the MOSFET may be derived from the MOSFET. MOSFET is the gate, work as metal or poly silicons. For insulator or oxide. And here, P-type silicons or N-type silicons. So, let's get. Yes, the substrate is just P-type. And it means the silicon is docked with lots of holes, not electrons. So, P-type silicon is working as a substrate. Then, if we induce some voltage to the gate, minus voltage, and for the substrate, positive voltage. Then, by the distortion and absorptions, the holes will just get closer to the outside. Okay, and second, the electrons will gather to the end of the substrate, but AB is small, so we can call it an accumulation state. The second, diffusions. So now we change the inducing of the voltage. Somewhat big voltage that can't over than the threshold voltage. Then by the diffusion of the force in the positive voltage, the carriers will not generate the surface of between the surface of the oxide and the substrate. So here we make the diffusion regions. And lastly, inversion. Let's get if it is about strong inversion. There is some positive voltage that induced over the framing as the threshold voltage, and the channel will be induced between the oxide and the substrate. So, if we look more to inspect split, then the partially between the oxide and the substrate surface will work as N-type. And the work or departing base will be work as P-type substrate or silicons. So this is how we see the MOSFET and how it works. So let's explain the MOS capacitor. The capacitance will change like this. Acceleration state, depletions, after depletion path, and when getting over to the inversion state, the capacitance of the oxide will be increased, and finally, saturate as the field of its maximum capacitance. At this state, from inversions. So this is the MOSFET. And for the PN junctions, I hope you know how it works. I hope how it works. So, see, we just these are the silicon that go as P-type, and in contrast side, in the opposite side, N-type silicon. So. After this, the electrons will move to the oxide side and will make the degenerations, and it means hole and electrons will assemble and they will be gone. So, the center between the P-type silicons and N-type silicons, this surface will make maybe lack of the carriers. So we call this region as depletion regions. So depletion region means there's only a few that maybe we can count or no carriers in this area. Of course, this means there is no carrier, but just for simply to say. So, 3 conditions. First, thermal equilibrium, and second, positive bias, and third, negative bias or the reverse bias. For a positive or forward bias, we induce the voltage for the positive voltage for the P-type substrate, and the negative voltage for the N-type side. Then the electrons of the P-type silicons, the minor carriers will move to the plus voltage induced wire, and the N-type poles, that is the minor carrier, and the silicons will move to the minus side. So we miss the depletion region will be more smaller. And second, the negative bias. So, for the reversely, we induce the minus sign and plus here, then what will happen? So the main carriers, the holes in the P-type silicons, will move to the outside of the left side to here, and the main carriers, the electrons of the N-type will move to the right side, the positive voltage side. So the depletion region will be more enlarged. it means no current flow. Okay, so lastly, about the mosfet. The MOS is derived from the mosfet. Maybe what the same function as the mosfet is, but a big difference between of them. So how the mosfet looks like? Let me take the example of the N-type MOSFET or N-channel type MOSFET of depletions. Sorry, the enhancement mode. For enhancement mode, so let's look. For the enhancement of the N-type MOSFET or N-channel MOSFET, in short, MFET, if the VG, the gate voltage is over than the threshold voltage, in positive bias, then the electrons of the piece of plate will be attracted to the gate voltage, and they will make the channel. So, if the channel induced, we can see that the switch is just closed. It means the current can flow. So, just one more thing. If we apply the voltage at drain source, sorry, the drain only heavy silicon, sorry, the heavy polysilicon of the N-type for the drain part, then the electrons will be attracted to the channels, electrons will be attracted to the positive bias here. But we know, if the electron move, then the current will be induced to the opposite movement of the electrons. So, the more strong the gate bias is induced, then it means the more gate bias induced, the more larger channel will be induced. Of course, if the gate voltage is over the threshold voltage, and for that, if the drain voltage is more bigger and bigger, then the example equation for the current density of the electrons, current density that induced by the electrons. So, that is part. The current flow density will be more stronger if the electric field is, in other words, if the voltage is more stronger, then the electric field will be more stronger. And it means the current density flow will be more larger. So it means the more current will flow through the channel as the gate voltage or the drain voltage has been enlarged or more stronger. And second, maybe the material components or how we just manufacture the device will be different. So for the mobility, with same power, how the electrons move more fast or more far. It means the mobility, in short, initially, and the charge, lastly, the density of carriers. Let's see. If we have a tunnel like this, let's guess. There is only two ways that cars can pass. Then at one time, only two cars can pass through this tunnel or not. But if we enlarge the tunnel and the road by double size, then at one time the 4 cars can pass. And if we accelerate the car speed, more cars can pass at the same time. So this is same as the density of current equations. So let's see if the gate voltage is over the threshold voltage. It will be like this. And will be saturation current. Okay, I hope you just how it works. I just hope how it works, you know. Okay, lastly, SS. So, threshold swing. So, threshold, sorry. For the ideal case, maybe the mosfet will work as like a switch. For the ideal case, maybe some vertical ramp off, like this. But in real case, we write here, it is not. Though we don't make any voltage that is under the threshold voltage, maybe by the diffusion effect, some little carriers can move from other side to the opposite side a little, and this will make the current flow, and it will make the device's power consumed or ineffectively. So it means if you're using a silicon, just get you're using a silicon, you just turn off the batteries and turn off the power, but after one day, when you check when you turn off the device, it was 44% of the batteries, and after you checked out, when you turned on, it was 39% of the battery. So it means that subthreshold thing is not good. It means though your device voltage is under the threshold voltage, the device keeps consuming the lower current, that though the voltage is not over the threshold voltage. So it means if the sub-threshold is good, then the power consumption will be more large, will be minimal. And if the sub-threshold thing is more bigger, the power consumption will be more bad. And the opposite. So, sub-threshold thing is very smaller, so we will look to instead of this factor as the logarithm or log size. So, the S can't be under the 50 millivolts per decade of the amperes by the Boltzmann's law. Okay, so next videos will be the topic of the short channel effect. Thanks for listening, and this is summarization of the fundamental of semiconductor calculus. Thank you.